right, up next, we have Benjamin Cumming, who's the Scientific Software and Libraries Group Lead at CSCS. He's going to be presenting developing and adapting scientific software for GPUs at CSCS. Benjamin, good morning. Welcome.
Well, good morning or good afternoon. So it's still morning time over here in Switzerland. So
well, it's almost midnight here.
So can everybody see my presentation?
I can see your screen. Perfect.
Okay. So good afternoon, and thank you very much for the opportunity to present today. So my name's Ben Cumming. So I was born, raised, and educated in Australia, but for the last 10 years, I've been working at the Swiss National Supercomputing Centre, CSCS. And over that time, we've been an early adopter of GPUs, and we have invested a lot of effort into porting applications to run on GPUs. So I'm going to be, today I'd like to share some insights that we have about, from this process. Because at PASC, we're going to be very soon, you're going to have a very large GPU-based system, the Satellix system. So a little bit about CSCS first. We are the Swiss National Supercomputing Centre. We have our headquarters and the machine room located in the southern Switzerland, in the Italian-speaking region, in the city of Lugano. And we have additional offices in Zurich, where most of the software developers working on the scientific applications are working. So CSCS is accessible for scientists around the world via open peer-reviewed calls. Very small proposals are allocated via a national call, and larger proposals are allocated via PASC, which is a European-wide allocation scheme. And international scientists from outside of Europe or Switzerland can apply for these, particularly for our national call. So CSCS was an early adopter of a GPU technology, driven by the same ultimate motivation of, facing power limitations with that meant if we want to continue getting more parallelism, we need to rethink how we do things. And HPC is a relatively small industry compared to other industries that use processors. So video games was the external market force that created this push to GPUs back in the day. So in 2011, when I started working, or just before I started working at CSCS, we had a system called 30, which was a Cray system with NVIDIA K20 GPUs, which we used for our early testing and development to start porting applications, because at this point we were on target to make our main system, our flagship system, PitStite, which was installed in 2013 with our 5,000 nodes. This was going to be a GPU-based system. So we started these programs to port and prepare our user program then. So this system was quite a powerful system at the time. It was number 3 in the top 500, and quite significantly, it was number 1 in the green 500. So it was the most energy efficient system in the world, which for such a large system that wasn't designed with that specifically in mind, that's quite an achievement. And the system has been upgraded since to more recent NVIDIA P100 GPUs, although these are starting to look a little bit long in the tooth. And as John mentioned earlier, CSCS was the first, or CSCS hosts the Swiss National Weather Service, the Swiss version of the Bureau of Meteorology. They host their system, and they were the first National Weather Service to go into using GPUs for their numerical weather prediction. So this is running traditional atmospheric modeling, atmospheric codes. But this was the start of a larger trend. When PitStite was installed, it was there were only a handful of systems in the top, at the high end of the top 500 that were GPU based. Now it's only a handful of systems that are CPU based. And not only have we got many GPU-based systems now, but the ratio of GPUs to CPU sockets is increasing. So we're getting more and more of our memory and compute is being provided by the GPUs. So I've got some ratios. We've got on the Cray-Schuster systems which are being installed. Cetinix is an example, but the Alps infrastructure we're building up at CSCS, Lumi the Lumi system in Finland, as well as the DOE pre-exascale and exascale systems, are all going to have this ratio of 4:1 for GPUs to CPUs as a rule. So this means that if we have an application or a code that we want to be running at scale on the largest HPC systems, it is now a hard requirement that, if we want to be doing that in 5 years' time with that application, we really it needs to be running on GPUs. But before, when I showed that Pitt Stein was number 3 in the world when we installed it, HPL is always the first application to get ported to run on a target architecture for obvious commercial reasons. But it can take a long time before the users of all the standalone applications on your system actually get the benefit of using GPUs. So it takes a long time to get a significant proportion of your users running on GPUs, because porting applications is really difficult, and also developing new applications from the ground up that are really targeted at GPUs is also very time consuming, because these old legacy applications have got a lot of features that you have to implement before you provide a useful service to your users. We realized that we had to really work with application developers, users, and vendors to over an extended period of time to be able to prepare our user community. And then there is no one magical approach for preparing users, because it really depends on the code, the domain, and the community, what approach you're going to take. We realized that we really needed to invest as a center in software development to really focus on providing development resources that would help our, to help our users adapt. I don't think we can just expect scientific applications to get updated for GPUs without investment or help from the computing centers. So I'm the lead of the Scientific Software Development Group at CSCS, which is a group of 34 people. I've got an out-of-date list of our staff members here. So it's a large group of people, and the key takeaway from here is that these are people who were hired to work as software developers. So their primary role is as software developers, and that's what their 9-to-5 work is. And they're collaborating with the scientific community. The main program we have for this is the PASC program in Switzerland. I think there's a new program starting at PASC, the PACER program, which I think is based on a similar concept. And this is where funding is provided to Swiss researchers who are developing scientific applications to hire postdocs and PhDs to work on the applications. And a significant part of that funding also goes to CSCS. And this team I showed you before funds many of those positions to then collaborate with the external scientists to help them with this process for preparing their applications. I suppose interestingly for the PASC crowd, 2 of the PASC projects, we've got 15 projects funded over a 3-year period at the moment, and 2 of those projects are related to the square kilometre array. Very interesting projects. So, when I started programming GPUs, or often, the approach that was espoused was, okay, I've got an application, I want it to run on the GPU. And the approach would normally be what you're told to do is, you have a look at which parts of you analyze the application first, you determine which parts need to be moved to the GPU, and then you go and do that. You allocate some memory using, your CUDA, something like your CUDA API, or maybe some OpenACC or OpenMP directives. You port the loops, you go through, you find the loops or the hotspots in your application, and you translate them to CUDA kernels, or maybe you add some compiler directives, or you use a different library call for your BLAS or FFT implementation. and then you do some manual memory movement. And now you have an optimized application for your GPU. Well, now what you actually have is two applications, because you've basically gone and changed the application. You'll have a different version of the application for CPU and GPU targets. And I want to make a note here that OpenACC and OpenMP won't actually solve this, won't actually give you one common unified code base, because what you'll find is you'll still have to go and modify a lot of the loop structures and the way the code is organized. Even with OpenMP, you might still end up with two different versions of a loop, or two different versions of the application that have been tuned to use OpenMP for the different target architectures. So this quickly becomes a bit of a maintenance challenge, because if another GPU architecture or another accelerator type comes out in the future, we might have to add further implementations. And so I recommend against just diving in, unless you can somehow put the resources that maybe some large weather and climate codes have put in over the years, where every 10 years they go through a massive process of porting to the new architecture. So an approach that we've found works best is this approach of separation of concerns, taking a step back and looking at an application and trying to first refactor or modify the application so that we take all of the performance critical parts of the application and we give them an interface which is domain specific. So an interface which provides an API or maybe provides a domain specific programming language that lets the domain scientist working on the front end of the application describe their problem in a using the domain specific language, the language that they're used to using, and then you can write multiple backends that don't touch this front end code used by the users, and then you can have the software development, software engineering experts work on the backends. Now, I've got an example here I'd like to demonstrate. So at CSCS, we've been focusing on NVIDIA GPUs because these are what we've had in our systems for the last, for more than 5 years now. But when you look at the code bases, some of the big code bases we maintain, I'm just looking at our GitHub statistics here, we see that CUDA is less than 3% of the GPU-enabled code in some of our code bases. One of the code bases here has 0 CUDA at all. And we generally have more CMake than CUDA in our applications. So I think if you're careful with the refactoring, you don't end up having to have an awful lot of domain-specific or architecture-specific code in your code base. So this might all seem a little bit abstract and vague, so I'm going to have a look at a couple of use case examples. So the first is a library called Sirius. Now, it was written as a backend for a very widely used application here in Europe called Quantum Espresso, which is a quantum chemistry application. It's a large Fortran 90 application which uses MPI and OpenMP, and it makes heavy use of BLAS, LAPARC, and FFT libraries. Now, when we first started looking at how we were going to try to add GPU support to this application, there are a few different options. One is just to directly intercept all of your BLAS, LAPARC, FFT calls and substitute them with the GPU accelerated equivalents. But because of the high cost of transferring memory between CPU and GPU each time, that was a non-starter. Your memory transfer costs would have swamped any benefits you gained from using the GPU. Another option is to work directly on the Fortran code with OpenACC or OpenMP. This would have required a very large refactoring. And directives, the main OpenACC has got very good support from one vendor, which is NVIDIA, but it's not widely supported on other architectures. And OpenMP, we're still waiting for OpenMP to reach maturity as a portable accelerator, the way of targeting accelerators today. And a very important consideration is we want to hire ambitious young developers to work on these applications. And it's very difficult to hire to hire young people to come and work on Fortran applications. And this is actually, one of the challenges is finding people to work on these codes. So this is actually something that's important to keep in mind. The other is to write a library that expresses these basic DFT building blocks in a standalone library. Now, a key point here is that all of the above approaches require significant investment. There's no simple way to do this. So Quantum Espresso was refactored. We created this library called Sirius, which provides this general purpose domain-specific libraries, and removed the low-level code from the main Quantum Espresso code. So now our domain scientists, they keep writing their algorithms up here in Fortran, and then calling out to the Sirius library. And our computational scientists at CSCS can really focus on developing this library here and its backends for the different architectures. Now, a key benefit of this type of approach is that because Sirius uses a domain-specific interface, not only is it used by Quantum Espresso, it's used by some other very important applications to us, the CP2K and Exciting, for example. And it provides quite a few different little interfaces that allow people to, that are relevant to this community, and that hide the actual implementation details, all of the different libraries and languages that we use for implementing the different backends. And these are some slightly out-of-date results, but they show a comparison of running Quantum Espresso on nodes which have got two CPU sockets, two Intel Broadwell CPU sockets, versus running on the same number of nodes with an NVIDIA P100 GPU and a CPU socket. And we can see that the key thing here is that we've now got very good, the GPU application is much faster for a given number of nodes. And I don't have the energy consumption here, but the energy consumption is also much lower. So we've taken a very large legacy Fortran application, and it's now running quite well on GPUs. So CSCS does maintain a version. We maintain both Sirius and a version of Quantum Espresso that has been refactored to use Sirius. And this has support for Intel CPUs, NVIDIA GPUs, and also AMD GPUs now via HIP and ROCm. The Quantum Espresso developers do actually maintain their own version, GPU version, which uses CUDA Fortran. I say CP2K, that should be Quantum Espresso. And that does get good performance, but it is less feature complete than Quantum Espresso Sirius, and it's not going to be portable to non-NVIDIA architectures like AMD GPUs. Second case study is a library called DBCSR. So DBCSR is a library for sparse matrix multiplication, but these matrices are very, very large and distributed, so they'll be distributed using MPI, and they have the special property that the non-zero entries are not scalars, but are small, dense block matrices. And we don't know a priori, the dimensions of these small blocks really depend on the model being simulated, and they can vary wildly. So they can be, dimensions of 17 by 4 by 3. So there's a wide range of these different matrix sizes. And DBCSR uses MPI and OpenMP for the distribution of the information and for scheduling the work. And it was developed as a sparse linear algebra backend for an application called CP2K, which is a very, very important application at CSCS. Many of our users run it. There's a GPU backend was implemented that does batched block multiplication. So it gets many of these small blocks, batches them together, and ships them off to the GPU to be multiplied. And it has a CUDA kernel that is used to implement this matrix multiplication that is heavily parameterized, so you can tweak it. And you really need to tweak a lot of parameters for any given matrix dimension, MNK pair, to get best performance. So DBCSR was implemented by the CP2K developers quite a few years ago, when they realized that they wanted to kind of remove that core functionality from being inline in the application and make a generic library for it so that they could port that more easily to the GPU. So the work I'm going to present today is the work of one developer at CSCS, Shoshana, and she performed the porting work done here over the space of about a year. So originally, let me just move here. So originally, the application they would try to guess a reasonable set of these M, N, K parameters for the different matrix sizes and do a lot of auto-tuning, which is a very, very expensive operation, auto-tuning to find the best possible set of parameters for each one of these matrix dimensions. They would then compile these into a massive library and into a very, very large library. And then when the application runs on the GPU, it would go into this, every time it needs to do matrix multiplications, it would pick the relevant implementation. And if there was no implementation available, it would it would just fall back and use a CPU-based kernel for doing the matrix multiplication. So the first step that Shoshana did is she said, well, if we don't have an available optimized kernel, we should be able to just-in-time compile one. So we can auto-tune the parameters ahead of time and store them, but we don't need to actually generate the code. And then at runtime, we can JIT only the kernels we need at runtime. And if we don't have a set of auto-tuned parameters, we can make a best guess. This reduces the compile times a lot and reduces binary size. And the key thing is here that it can generate code for any combination of M, N, K parameters, so long as good parameters are available. So if you've done some auto-tuning for a particular set of parameters, you're in luck. But if you haven't, how do you come up with an estimate, a good set of parameters? And the solution was to use machine learning. So for a given GPU model, perform some auto-tuning on a set of parameters, and then she used boosted regression trees to then train a model that could predict parameters for that could then predict or estimate good parameters for when they were needed. This training does require significant GPU resources, but significantly, it required far less resources than the process of auto-tuning all the parameters did. And the results were very good. The parameters that were given by the parameters that the machine learning model came up with were generally within 3% of the auto-tuned kernels on average. And this is very important because once you don't just tune the application, you don't just tune these parameters once, for example, and in NVIDIA GPUs, every time NVIDIA or AMD release a new GPU model, you have to go and retune all of the parameters. So this makes it very much easier for us when we have to target a new GPU type to a new GPU architecture, not just from the different vendors, but from the same vendor. And here's just some results showing that we had an MI50 AMD GPU and a P100 GPU were on par, which was good to see because we get good performance for both of those architectures. Now, AMD GPUs are of course something that's very interesting to everybody at PASC, and the last slide there showed results for AMD MI50 GPUs, but I've been talking about CUDA so far. And the CUDA backend, the original CUDA backend, took quite a few years and a lot of effort to develop because of the initial upfront cost of the library design. But the AMD HIP backend took 21 days to write for Shoshana when she sat down to do it, because the application uses code generation to generate these kernels. So we didn't have to go and port a whole heap of our CUDA kernels. Instead, we just had to port the code that generates the kernels to generate HIP kernels. and also had to do some basic wrapping, changing CUDA API calls to HIP API calls. So there was a large initial investment in developing this DBCSR backend by the CP2K developers. But now we're seeing that CP2K can be adapted to new accelerator platforms quite easily, or very, very easily, relatively speaking. And CP2K will still be running on the biggest systems in 10 years' time as a result of this effort, which is going strong for a so-called legacy Fortran application. So my quick conclusion here is that before diving into trying to adapt to GPUs, it pays to make an upfront investment in refactoring the code to use a domain-specific library interface that can be used by the front-end application that basically hides the implementation detail from the front-end users. And I see that I'm running a minute over, so I'll finish up there and see if anybody has any questions.
Thanks, Benjamin. I do have one question that came in. With the abstractions that you create, i.e. for Sirius, does your team aim to keep most of the application state on the GPUs, or do you also stream state in and out of the GPUs from main memory? I can imagine the former approach would limit problem size, but the latter approach would limit gains. I'm curious to know which approach works better for you.
This is, as I said, there's no silver bullet. I mean, for weather and climate applications, we found, for example, that you had to keep everything on the GPU. We had, for example, in the Cosmo weather code, that's 250,000 lines of Fortran code, and it had 80,000 lines of Fortran code that took 1% of the time to solution. But we still had to port that to the GPU because we found that the cost of copying all the fields, pressure, velocity, temperature, et cetera, back to the hosts to do that little bit of data assimilation blew away all of the gains we made from converting everything to run on the GPU. The DBCSR library I just showed you there, that keeps all the state on the CPU, but then it uses very efficient methods to batch up these multiplications and send them in chunks so it can overlap the copying of data between host and device. Sirius also uses some similar approaches like that. The GPUs that are going to be on Cetonix and the next generation GPUs that we're seeing coming down the pipeline have got a lot more memory, and the ratio of CPU memory to GPU memory is changing, and we're also going to have much better access between CPU and GPU memories. So which approach you choose I think is going to change based on these new constraints.
Okay, thank you, Benjamin. Appreciate it.
No worries.